There are different ways that we can put our components together in order to make a circuit. All right. So we've got resistors, inductors, capacitors, EMF sources. All right. How do we put these things together to do things? Well, that's what I mean to say. There's a lot of different ways to do this. So what I want to do here is just sort of give you some bird's eye view of what these things could be like and how we talk about them, because it's important to understand how we talk about them so you know how to interpret them and how to handle them. Okay, so let me make a little circuit here. All right, so I'm going to put an EMF over here, and we're going to let it come up. It's going to go through a resistor. All right, then there's going to be a split right here. I'm going to put a resistor there, and I'm going to put an inductor up here. Then we'll come back together, and let me put a capacitor here just for grins and giggles, and then we'll close it off like this. Okay, so some of the things that you probably caught there already, all right, in terms of how we talk about things. So I talked about having a split. All right, so here's one split. We come here and here. Okay, so whatever current we have over here, like suppose we have 10 amps here, then we're going to have something like 4 amps here and 6 amps down here, because that 10 has to go somewhere. Part of it goes one way, part of it goes the other. Now, figuring out how much goes one way and how much goes the other, that's a whole different thing, and we're not going to worry about that right now. I just want to introduce that idea to you that we can have that, and then hopefully you can see also that they have to come back together like this. Okay, now these things can be really, really crazy. All right, we could have a split on a split on a split. Okay, if we wanted to, we could have our circuit come along and it splits. There's a three-way split, it comes back together. All right, maybe there's a split, a two-way split here, and then this one just comes straight across. You know, maybe I've got resistors in here, inductor, capacitor, whatever, and they all come back together. So we can have lots and lots of different splits like this. Okay, now the thing to remember when we have a split is how the current on the two sides has to be equal. Okay, so 10 becomes 4 and 6, 4 and 6 turn back into 10. Okay, just sort of like that. Now another idea here is the idea of a loop. Okay, and so in this first circuit I've drawn, all right, we have 2 loops. Okay, so I've got a loop here, and then I've got a loop also in here, just like that. Okay, now in the one I've got down below, you can see that I got 1, 2, 3, 4, 5, 6, 7. I'm probably missing some. Okay, there's a whole bunch of loops in there, and the reason that's important to be able to see those as loops is because there's certain ways of analyzing circuits in which having those loops is very, very important. Okay, and that has to do with something called Kirchhoff's laws, which we're not going to get into right now. All right, but it's important to be able to see those things as they are. Okay, so now let me do a bunch of undos here. Boom, 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 boom. Keep going, keep going, keep going, keep going, keep going, keep going. Almost, almost, almost there, and there we go. Okay. All right. So another important idea is the idea of voltage drops. Okay. Now a voltage drop, you need to think about our artificial stream. Okay. The pump pumps the water up, and then that water from there goes through a series of actual physical drops. Okay, as the little waterfall goes, you know, maybe it goes down a foot, then maybe it goes gradually, but goes down 2 feet, and then a big drop, it goes down 2 feet, then it gradually goes down 3 feet. Okay, so it's a sequence of drops to get to the bottom. All right, and once we get to the very, very bottom of the pool at the bottom there, then we've dropped, however much we've dropped, maybe 15 feet, we know that the pump had to take us up 15 feet to begin with. All right. So that's a voltage gain. and then we've got little tiny voltage drops, okay? For the water, it's a height gain, height drops. For our circuit, it's a voltage gain and then voltage drops. All right, so here I'm going to have a certain EMF. Okay, so I'll just write it like this. So that's a voltage gain. We go up. That's like our pump with the water, takes us to the top pool. And then we go down our first little tiny waterfall, okay, which is a height drop for water, a voltage drop for our circuit element. Then across this whole thing where we've got this split, we've got another voltage drop there, okay? And then we might have another voltage drop down here, okay? So, but what we can know is that delta V1 plus delta V2 plus delta V3 has to equal up to what our gain was, all right? So maybe, 3 feet down, 5 feet down, 7 feet down. We went up 15 originally. 3 plus 5 is 8 plus 7 is 15, okay? So we have a voltage increase, and then we get voltage drops as we go around our circuit, all right? So again, this is just a view from 30,000 feet, okay? So I'm trying to get you used to a way of thinking about circuits and some important ideas in there, all right? Okay, so now let's talk about, we're going to skip ground loops for just a second and hit parallel and series. Let me get rid of all those things. Boom, 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 boom. Okay, so parallel, okay, if two things are parallel, they're like running side by side, right? So here's the language that we use. This inductor and this resistor are elements that are in parallel, okay? So if you hear something that's in parallel, you need to automatically picture, oh, I had a split. Now I've got my things, and then they're going to have to come back together, okay? Split, they run in parallel, then they come back together, okay? That's parallel, all right? Things that are in series are sequential. First one, then the next, then the next, okay? So item 1, item 2, item 3. So my resistor, my parallel inductor-resistor combo, and my capacitor are all connected together in series. Okay? They're connected together in series. So let's do something. Let's try to illustrate this just a little bit. So I might have a capacitor and a resistor in parallel, but I put a resistor and an inductor in parallel. Within that, across the top, I'm going to put a resistor, capacitor, and an inductor like this, okay? So this could be a little bit tricky to try to say, but what I have here is I have a resistor and capacitor and inductor in series together that are in parallel with a capacitor that's in series with another inductor and resistor in parallel. Okay, so me saying it out loud like that, it's kind of like, okay, but if I wrote it down, you'd be able to kind of decode it and figure out what it is, okay? So after this video, I'm going to have some exercises that go with it to help you kind of begin to put this language together with what things look like, okay? So parallel, they're running together somehow. Series, they're sequential. Okay, now another important idea here when it comes to parallel things, all right, we've got the same voltage on those items, the same voltage difference, okay? So if I call this point A and I call this point B, the voltage across my inductor and the voltage across my resistor are going to be the same. They're going to be the same. The currents will be different, but the voltage across them will be the same. All right. So it's kind of like, imagine our waterfall again. So we got a pool at the top, water's coming down. But imagine we build in a split. Okay. So the water comes apart and then it goes back down. Okay. And it meets back up before it gets to the end. Okay. So we're up here, try to hide. Okay, the water comes down, splits up, and then it meets back up again. Okay, so at our split, maybe there's a 5-foot drop, but they both drop 5 feet. Okay, even though they might go totally different, once they come back together, they've still both dropped 5 feet. Okay, so whenever we've got items in parallel, they're going to have the same voltage on them. Okay, now items that are in series, on the other hand, they can have different voltages across each one, but we're going to have the same current in those. Okay, we use the letter I for current, same current in those. All right, and basically what that means is, again, if we think about the stream, okay, so I got my stream here, I'm coming down, I'm going to split, and then I'm going to come back together. Okay, if I've got 30 gallons a minute up here, all right, down here later on in my stream, I still have to have 30 gallons a minute. All right, if I come in with 40 gallons a minute, and later on I only have 30 gallons a minute, I got 10 gallons per minute that just disappeared. Okay, on the other hand, if I had 30 up here and I have 40 down here, then I got 10 gallons per minute that just magically appeared. All right, how does that happen? Okay, well, it can't, okay, unless there's some trickery going on, some black magic that we're not used to. Okay, switches, those are pretty straightforward. A switch is just going to be where, you know, somehow we put a break in our circuit, and usually, you know, you mark a switch something like this. Okay, and there literally you can see if it's open. All right, the switch is open. That means the circuit's open. All right, and so nothing's going to flow. If the switch is closed, then things can flow. Okay, so kind of another way to think about open and close there. Okay, now let me get to ground. Okay, get rid of all this stuff. I need a new drawing. Okay. Okay, now you see this a lot more with actual schematics and stuff like that, but just for funsies, I'm going to do one with alternating current. Okay, so we got an alternating voltage source here, and let's have a resistor in series with 2 capacitors that are in parallel, and those are all in series with an inductor. Okay. Okay, now what we do sometimes is we just go ahead and connect them back together just like this. Okay. However, that does, in the real world, that's not always practical, and it's not always safe. Okay. And so for reasons of practicality and safety, a lot of times what we do is we actually use Mother Nature. Okay. And so there's one side of my voltage that comes out over here. Okay. But the other side actually goes into a little thing we write like that. And that's what we call ground. Okay. Now that literally means the earth, dirt. Okay. So if something's connected to ground, that means it is physically connected through a wire to a pipe in the ground, or a big stake that's driven in the ground, or a pole or something. It's connected to the earth. All right. And then what we would do on the other side is we would connect that to the earth as well. Okay. Now, in this case here, even though it looks like it might be an open circuit, because like, how is it connected? Well, it is actually connected because of the earth. Okay. And the earth can allow electrons to come in and out on this side, and also on this side there. Okay. So the earth can be loosey-goosey with its electrons. Earth is so huge. All right, we can move electrons around, and it doesn't really make any difference for the earth. Okay, we put them in, we take them out, we put them in, we take them out, put them in, take them out. Okay, and so this is what we're doing there. So, for example, if we look at an electrical outlet here. Okay, I'll try to see one, get the picture right. I can't see one right away. Okay. Still, I don't have one in sight. Crap. But, you know, they tend to look like this. Okay? They look like this. And so we got two slits and a dot and a hole. Okay? And so the way this works is the smaller slit, and I'm not sure if it's on the left or right. That's what I was trying to look and see. I apologize. You can look. Whichever one is thinner, okay, that is connected to the top of an alternating voltage supply. Okay. This guy over here on this side is just connected to ground. Okay. That's connected to ground. So if you plug in a lamp, let's say, here's my lamp. All right, I plug this thing in. Okay, I'm going to be connected to the hot side. It's going to come in, go up through there, and it's going to come out and go on that side right there. Okay, now if I break one of those wires, I'm going to have an open circuit. No light's going to flow, but that's the deal. Okay, so if you are a person, let's say here, okay, you're standing here, all right, and maybe you're a small person, maybe you're 2 years old, and maybe you have your dad's car keys like I did, and you take said car keys and you plug them into the only slot they fit in, which is the big one. Okay, now I'm connected here, and I'm connected to the ground. Nothing happens. Okay, and I'm here. I didn't die. I didn't even get shocked. Okay, because there's no juice on that side. Okay, there's no voltage source on that side. It's connected right to ground. Okay, now, however, let me back this up. All right, I'm still connected to ground. If I had done the hot side over here, if I'd connected that, then I would have completed the circuit and current would have flowed from me to the ground. Okay, and I would have got a bad, it wouldn't have killed me, but I would have got a bad shock and that kind of thing. But you know, if you were in the bathtub or something, you couldn't get out in time, then you might be risking death. But anyway, so the two slits there are different. Now, let me get rid of all that with my little danger self there. Okay, now let's talk about this third wire. Okay, the third wire here in the cord to your appliance, if it's got a third wire, it's actually hooked to the outside, and often it's called the case ground. Okay, it's called the case ground like that. And on the inside, that it goes right to the to ground also. Okay, that's only a safety feature. Okay, if you've got, especially if you've got a metal box or something like that, what happens is as the cord, as an electrical cord gets yanked around and whatever it is, your appliance gets used, you might end up fraying part of the wire right down here. And then you wouldn't necessarily know it, but you might be hanging on to it, holding it, and you might go to plug it in, okay, and you're going to get a nasty shock, okay, because the electricity is going to go from the hot wire, okay, around and to you if you're holding it, okay. You could get a dangerous shock that way, all right. What the case ground does is, whoops, I lost my head. If that happens, if you get a fray and there's a short in your cord, then the electricity actually goes this way. Okay, and then your circuit breaker blows. So you plug in your whatever it is, your toaster or something, and then you know, the lights go out and you got to go down in the basement, flip some switches, and get the electricity to come back on. Okay, so when that happens, it's that happens as a safety feature. Okay. And it's just, you know, to try to keep you from hurting yourself. Okay. All right. So there we go. Lots of stuff there. So at the end of this video, I'm going to have some exercises for you about parallel and series components and some things like that for you. All right. The better you kind of get familiar with all this stuff, then the easier things are going to be once we get into all the details. Okay.